In this video, we're going to explore the concepts presented in Experiment 3, Introduction to Data Analysis. In this lab, we are going to continue our focus on building a laboratory safety mindset by practicing wearing appropriate personal protective equipment in the lab. We will also look at laboratory equipment to determine what kind of SI units they employ and the precision and accuracy they provide us when making measurements. Lastly, we will work some multi-step problems by applying dimensional analysis. A couple of housekeeping notes for this lab experiment. While we will only be working with water this week, to help you build lab safety practices, you are required to wear scrubs and goggles during lab. You should also wear gloves anytime you're working in the lab as well. Because we are only working with water, any waste at the end of the lab can be poured down the drain. It is also important that you clean the glassware you will be using both before using it and when you are done with the lab. Starting with clean glassware will reduce contamination in your work by ensuring you start off without any substances in your container. Never assume that glassware you see in the drawer, on a counter, or on a shelf was put there by someone else clean. When you finish, please make sure to return all of your glassware to the appropriate drawer, clean and dry. An important part of taking measurements and recording data in chemistry lab is looking at the units. For almost all numbers you're going to record in this class, you will need to write down the units that go with them. Without them, the numbers are meaningless. If I have the number 4 written down, am I talking about 4 grams, 4 milliliters? What does it mean? Always include the units. This will also help when you're doing problems. Many of the problem-solving skills you'll need come from looking at the units you're given and looking at the units you need to answer and figuring out how to get there from one to the other. Let's look at an example. How many inches are there in 2.5 miles? When I'm faced with a problem that looks like it's going to involve unit conversions, I start writing down all the different unit conversion factors that I know involving the units given. So in this case, I know that 12 inches are in 1 foot. I know that there are 3 feet to 1 yard. And I know that there are 5,280 feet in 1 mile. Now it may be that I write down a unit conversion factor that I'm not going to end up needing. But it's usually easier to have all of the things that you might need written down before you start the problem. So we're going to start off by looking at the number of inches in 2.5 miles. So we need to say to ourselves, well, we know we have 2.5 miles. That's a number in a unit that we're given. And then I know from my list up here that we've got a unit conversion involving miles and feet. I also know that I want miles to cancel out, so miles will need to go on the bottom. And from our unit conversion up here, we know that in 1 mile, there's 5,280 feet, so that's going to go on top. And if we look at our units, we can see that miles will cancel out, and we're left with feet. But that's not inches yet, so we go back and we look back at our unit conversion factor, and we see, do we have another one that involves feet and inches, which we do. We know we need feet to cancel out. So in 1 foot or feet, we have 12 inches. And we see that that unit's going to cancel out as well. So at this point, the only thing that I'm left with now is inches. And to find the answer to that, I just need to multiply across. So we take 2.5 times 5,280 times 12. Divided by 1, and this is all left in inches. If we multiply that all together, I get 158,400 inches. Now, the next thing I need to do is write this number in the correct number of significant figures. And if we look back at our values used, we know that 12 inches is an exact number, so that this isn't involved in our sig figs. And we look back again to our original problem, we have the number 2.5. So this tells me that I need to give 2 sig figs in my final answer. Well, the only way to do that with such a large number is to use scientific notation. So I'll write 1.6 times 10 to the 1, 2, 3, 4, 5. 10 to the 5th inches. And this will be my final answer. Notice that I have the correct number of sig figs and I've included the unit in my answer. As it turned out, I didn't need to know that conversion from 3 feet to 1 yard, but it doesn't hurt anything to have a little bit of extra information. So in this lab, we're going to be measuring physical quantities. Those physical quantities that we'll be measuring are mass, volume, and the object's dimensions. We are also going to look at the reliability of the measurements that you make in the lab. And the reliability of those measurements depend on two things, both the quality and the accuracy of the instrument or glassware that you're using, and the skill of the experimenter. We understand that many of you have not used some of the glassware and equipment that you'll be using in this course, and that's okay. There are instructions in Chapter 3 of the lab manual, and your TA is always there to help. We also need to worry about significant figures. You should always record all of the significant figures you have when making measurements. For example, when using the balance, if it has 4 decimal places for the mass, you should write down all of the decimal places, even if you think you're probably going to be rounding to one significant figure. Again, it's better to have too much information than not enough information. When looking at glassware, you should always estimate one additional decimal place beyond the markings on the glassware. Always assume that the last digit is in fact an estimate. Let's look at an example. So if we have a graduated cylinder, I'm going to draw some markings. We'll say that this is 2.0, 2.1, and 2.2. When we pour a liquid into the graduated cylinder, it forms a meniscus or a slight curve. Now, when I'm measuring the volume here, I see that it's going to be at least 2.1 because the meniscus is above the 2.1, but I can estimate how far it is between the 2.1 and the 2.2 mark. So to me, it looks to be about halfway, so we'd say it's 2.15 milliliters. It's assumed that the 5 is estimated. If I were to write the number as 2.1 milliliters, then someone looking at my data would assume the 1 is estimated. But we know that it's 2.1 something based upon the markings on our graduated cylinder. And we don't want someone to think it's just 2.1. We always want to estimate one decimal place beyond the markings on the glassware. And if you don't remember them, you probably need to review the sig fig rules in your textbook. There's a few things you need to look at, including the non-zero digits, zeros, dealing with exact numbers, things like there's exactly 12 inches in a foot, addition and subtraction rules, and multiplication and division rules. If you need help with these, check with your TA or go to the Learning Center for more help. We're also going to be evaluating two different things in this experiment, precision and accuracy. These two things mean something very, very different. Precision means how close your values are to one another. So if I record a mass with a sample 5 times and I have a very low standard deviation, I can have high precision. That tells me all of my values are very close to one another. Accuracy, on the other hand, tells us how close our values are to the accepted value. So if I have a low % error, that tells me that my experimental values were close to the accepted values. There are other videos which will demonstrate how to do these calculations, so you can ask your TA or go to the Learning Center for more help. So now we're getting to density, which is what we're actually going to be determining for our aluminum foil. We're going to use the mathematical combination of mass and volume. In general, most liquids and solids, it's reported in grams per milliliter. Density is an intensive property, meaning it doesn't matter if I have 10 mils, 100 mils, or 1 liter of something. If it's the same solution, the density will be the same as long as the temperature is constant. For example, water has a density of 1.00 grams per mil at 20 degrees Celsius. This does change with temperature, but only slightly. You may remember from your math class that you can measure the volume of an object by measuring its dimensions, or its length times its width. If we have a cube, that's pretty easy. But let's think about if we have some kind of odd-shaped object, because we don't often work with cubes. So we're going to have to use a technique called volume by displacement. That's where you measure the volume in a container using something like a graduated cylinder that's very accurate. You can then add the object and then measure the volume of liquid after. The change in the volume of water, or whatever solution you're using, will then be the volume of the object that you placed inside it. There are a couple of conditions you have to be concerned about when measuring the volume by displacement, because these things can happen. First, the liquid must not be one that will react with a solid in the time frame of the experiment. So if something will have a very slow reaction over a number of days, it will be okay to measure in it, because your solid's only going to be in there for a few seconds. The second condition is that the density of the solid must be greater than that of the liquid, so that it will sink down into the liquid. If it doesn't sink and if the solid's still floating on top of the liquid, then you're not truly getting an exact volume of that solid. So you have to make sure that your solid will sink in the solution or the liquid that you're using. We can also determine density using the graphical method. So here's an example graph of some data for some mass and volume measurements that have been recorded. If we look at the data points, we can see that we have mass on the y-axis and volume on the x-axis. Remember that equation for a line, y equals mx plus b, where m is our slope and b is, of course, the y-intercept. Remember that saying, rise over run? Remember, that is just the same as saying the change in y over the change in x. So if we're looking at our graph, if we look at the slope, we're going to have the mass over the volume, which is the definition of density. So when we look at the formula for a line, we see that we have m, which is the slope, which is the same as the density. If we look at our graph and we look at the data that we generated by the graph, the slope will be the density of our sample. There's a couple of things you want to make sure you watch out for when you're in lab. You need to pay attention that you are seeing this change in your mass, so that these numbers are all increasing, and that you have at the same time a change in the volume. If you're not seeing a change in the volume, you're going to end up with a bunch of data points that will form a straight line, and that's not going to be helpful for you. The same is true as if your mass is not changing. You don't want to form a straight line. You want to make sure that you pick pieces of aluminum foil that are different sizes, so that you can have a different mass reading through each one of your measurements. Now, for this experiment, you'll need to write a procedure. So the best thing to do is to start by reading the introductory material in the lab manual on Chem 21 and read the data analysis questions at the end of the experiment in the lab manual and determine the data that's needed to answer those questions. You will need to pull in what you learned in experiment number 2 about how to use the lab equipment that's available in the lab. Start off by making a list of all the information you need, including things like density, and, well, how to find the density. You'll need mass and volume. Think about some of the following things. Measuring multiple samples of multiple sizes. Think about what the graph would look like if the pieces of aluminum foil are all the same size, and therefore will have the same mass and the same volume. You'll need to think about the shape of the foil. Does that matter? Do you need to crumple it up into a ball, or will you want to roll it up? And what kind of glassware is needed? Are you going to need to use a beaker or a graduated cylinder? And if so, what size of those glasswares is needed? As a general rule, you'll always want to use the smallest glassware possible as it tends to be the most accurate when dealing with volumes you're measuring. You do need to write the procedure with enough detail that someone else could repeat the experiment with only your procedure and get similar results. Explain each step that you take. If you record the volume by measurement, explain how you do that. It's okay to change your procedure as you're going through the experiment. It's only the final procedure that goes into your lab report. So, if you get into lab and you realize something's not working the way you thought it would, make the change. Write it down and include the change in your final version. You also need to keep a lab notebook. The best thing to do before you come to lab is to set up the lab notebook. If you're going to need tables for your data, such as your mass volume pairs for different samples, set up the table and make a list of the data that you need. Write in the units, draw lines or boxes where you're going to fill in the numbers later. The goal is when you come to lab, you're just going to be filling the numbers and not having to write a bunch of information. This will save you a lot of time and frustration because it makes sure that you have all the information you need before you leave class. There are example pages in your lab manual showing what lab notebooks should look like before you come to lab and after you leave lab. Please look at these examples. Just like with the procedure, it's okay if it's not perfect when you come to class. Make a single line to mark out the incorrect information and rewrite the new information. It doesn't have to be perfect. Lab notebooks are meant to be the original record of your data and should be just that. Don't feel the need to rewrite them, to write on a scratch piece of paper or copy it into your lab notebook later. Just record the information directly into your lab notebook. If you have questions or you need help with the procedure, the experiment, or anything else, please talk to your TA, go to the Learning Center, or talk with the lab supervisor.